What you're looking at right now should be impossible. This is a photograph of something that by definition cannot be photographed. A black hole. That glowing ring? That's the last light you've ever seen before crossing into a realm where time stops, space tears apart, and the very laws of physics break down. In the past decade, we've gone from speculation to sensation. We've heard black holes colliding from over 1 billion light years away. We've photographed their shadows. We've watched matter accelerate to 99% of speed of light as it spirals to its doom. But here's what will blow your mind. If you fell into one of these cosmic monsters, you wouldn't just die. You'd experience time itself coming apart. You'd be stretched like spaghetti while watching the entire future of the universe flash before your eyes in seconds. And that's just the beginning of how weird black holes get. This is the story of humanity's most mind-bending discovery. How we went from 18th century speculation about dark stars to realizing that black holes might be holographic projectors, cosmic recycling centers, and possibly even doorways to other universes. By the end of this video, you'll understand why black holes aren't just objects in space. They're the key to understanding reality itself. I'm John, and welcome to the most extreme journey in physics. Buckle up, we're about to dive into the heart of darkness. Our story begins not in the 20th century with Einstein, but in the candlelit studies of the 18th century England and France. Picture this, it's 1783 and Jean Michel, a brilliant clergyman, who has also happened to be one of the era's greatest natural philosophers, is having what might be history's most prescient thought. Michel knew that the speed of light was finite, though barely. He also understood Newton's law of gravitation. So he asked a simple but profound question. What if a star was so massive that its escape velocity exceeded the speed of light? Light, he reasoned, would be like a cannonball fired upward. It might escape a small star, but a massive enough star would pull it back down. Simultaneously across the English Channel, Pierre-Simon Laplace was reaching the same conclusion. In his exposition Du Système du Monde, he described invisible bodies whose gravity was so strong that light couldn't escape them. He even calculated that a star with the same density as Earth but 250 times the Sun's diameter would trap light completely. But here's the beautiful irony. They were right for the wrong reasons. They treated light like lit particles that could slow down and fall back to the surface, like throwing a ball upwards. We know light always travels exactly 299,792,458 meters per second in vacuum. It never slows down, never speeds up. So how can massive objects trap something that always moves at light speed? The answer would have to wait 130 years for a young patent clerk in Switzerland to revolutionize our understanding of space and time itself. Einstein's 950 general theory of relativity revealed that massive objects don't pull on light. They warp the very fabric of space-time. Light still travels in straight lines, but when space itself is curved, those straight lines can curve right back on themselves, creating a gravitational prison from which nothing can escape. Just months after Einstein published his field equations, Karl Schwarzschild, a brilliant German physicist and astronomer, was serving as soldier on the Russian front of World War I. Despite the chaos of war, Schwarzschild worked out the first exact solution to Einstein's equations, describing the space-time around a spherically symmetric mass. Tragically, Schwarzschild died of an autoimmune disease just months later, but his mathematical legacy would outlive empires. His solution contained something strange, a critical radius where the curvature of space-time became so extreme that the mathematics seemed to break down. This Schwarzschild radius would become the mathematical definition of a black hole's event horizon. Here's what's fascinating. For decades, most physicists thought Schwarzschild's solution was just a mathematical curiosity. Even Einstein himself believed that nature would never allow such extreme conditions to exist. They called them frozen stars, collapsed objects, dark stars, anything but black holes. The general consensus was that these interesting mathematics with no physical reality. It wasn't until the 1960s, nearly 50 years after Schwarzschild's work, that physicists John Wheeler, Stephen Hawking, and Roger Penrose began taking these solutions seriously. Wheeler coined the term black hole in 1967, and suddenly what had been a mathematical curiosity became the focus of intense scientific investigation. Today we know that Michel's 18th century intuition was more prophetic than anyone could have imagined. The universe is teeming with black holes, from stellar corpses to supermassive monsters that dwarf our entire solar system. So what exactly is a black hole? Forget everything you think you know from science fiction. A black hole isn't a cosmic vacuum cleaner or a hole in space. It's a region where gravity has become so intense that it fundamentally alters the structure of space-time itself. Let's start with the most famous feature, the event horizon. This isn't a physical surface you could touch, like the surface of a planet. Instead, it's a boundary in space-time itself, the ultimate point of no return. Cross this invisible line, and every possible path you could take leads inevitably inward to the center. Here's a mind-bending way to think about it. In normal space, you have a light cone of possible futures. All the places you could potentially reach given the speed of light limit. Near a black hole, these light cones tip inward. At the event horizon, they tip so far that even light rays pointing directly outward actually curve inward. There's literally no direction you can point that leads back to the outside universe. This size of boundary depends entirely on the black hole's mass. A black hole with our sun's mass would have an event horizon just 6 kilometers across, smaller than Manhattan. But the supermassive black hole at our galaxy center, Sagittarius A star, has an event horizon about 24 million kilometers across, roughly the size of Mercury's orbit around the Sun. If the black hole is spinning, and most are, things get even weirder. Spinning black holes drag space-time around with them, creating a region called the ergosphere, where space itself is rotating. Inside the ergosphere, it's impossible to remain stationary relative to distant stars. You're forced to rotate along with the warped space-time. Inside the ergosphere, it's impossible to remain stationary relative to distant stars. You're forced to rotate along with the warped space-time. Remarkably, this rotation makes it possible to extract energy from a black hole through the Penrose process, a theoretical method where you could drop an object into the ergosphere, split it in two, and throw one piece into the black hole, where the other escapes with more energy than you started with. The black hole pays for this energy by spinning slightly slower. At the very heart of every black hole lies the singularity, a point where our best theories completely fail. According to general relativity, all the black hole's mass is crushed into a point of infinite density and zero volume. The curvature of space-time becomes infinite. Time and space lose their meaning. But infinity is physics speak for we don't understand what's really happening here. Most physicists suspect that quantum effects we don't yet understand prevent true infinities from forming. We need a theory of quantum gravity, a unified description of quantum mechanics and general relativity to understand what really lies at a black hole's heart. Now here's what black holes become anything but dark. Matter falling toward a black hole doesn't just disappear quietly. It puts one of the most spectacular light shows on the universe. As matter spirals inward, it forms an accretion disk, a swirling maelstrom of gas and debris orbiting a significant fraction of light speed. As matter spirals inward, it forms an accretion disk, a swirling maelstrom of gas and debris orbiting at significant fractions of light speed. The friction between different parts of this disk heats the material to millions of degrees, so hot it glows in X-rays. The inner edge of the disk can reach temperatures of 100 million Kelvin, making it one of the hottest environments in the universe. A sugar cube-sized piece of this material would release more energy than an atomic bomb. But the real cosmic fireworks come from the jets. Some black holes launch narrow beams of particles at nearly the speed of light, stretching for thousands of light years across the cosmos. These relativistic jets are powered by magnetic fields that get twisted and amplified by the black hole's rotation, creating cosmic particle accelerators that dwarf anything we can build on Earth. Black holes come in a fascinating variety of sizes, each with its own history and story of formation and evolution. Stellar mass black holes, typically ranging from 30 times to 50 times of our sun's mass, are the corpses of most massive stars. When these stellar giants exhaust their nuclear fuel, they collapse catastrophically, leaving behind black holes that can survive longer than the universe itself. Supermassive black holes are the titans of the cosmic deep, monsters weighing millions to billions of times more than our sun. Every large galaxy seems to harbor one at its center, and their formation remains one of astronomy's greatest mysteries. How did they grow so large so quickly in the early universe? Between these extreme lie intermediate black holes, a population we've only recently begun to discover. These might form the collapse of every first stars in the universe, or through the collision of smaller black holes in dense stellar clusters. Most exotic of all are primordial black holes, theoretical objects that might have formed from extreme density fluctuations in the first fraction of a second after the Big Bang. These could range from microscopic to stellar masses, and some scientists speculate they might account for some or all of dark matter. To understand how black holes are born, we need to follow the epic life cycle of most massive stars. Cosmic behemoths that live fast, die young, and leave spectacular corpses. Every star's life is a constant battle between two fundamental forces. In the core, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy that push outward. Gravity pulls everything inward, trying to collapse the star. For most of a star's life, millions to billions of years, it's a perfectly balanced struggle. But here's the cosmic irony. The most massive stars, which have the most nuclear fuel, actually burn through it the fastest. A star like our Sun will fuse hydrogen steadily for about 10 billion years. A star 25 times more massive will exhaust its core hydrogen in just a few million years. A cosmic blink of an eye. When a massive star starts running out of core hydrogen, it doesn't give up, it gets creative. The core contracts and heats up until it's hot enough to fuse helium into carbon, oxygen. When the helium runs out, it fuses carbon into neon and magnesium, these oxygen into silicon and sulfur. Each stage burns faster and releases less energy than the last. Hydrogen burning lasts millions of years. Helium burning lasts thousands of years. Carbon burning, centuries. Oxygen, years. Silicon, days. But then the star hits the ultimate wall, iron. Iron 56 has the highest binding energy per nucleon of any element. Fusing iron into heavier elements doesn't release energy, it requires energy. When the core becomes iron, nuclear fusion stops dead. The star has seconds to live. What happens next is almost impossible to comprehend. The iron core, about the size of the Earth, but with about 1.4 times the mass of the Sun, suddenly loses the radiation pressure that was holding it up against gravity. In less than a second, literally faster than you can blink, the core collapses from 7,000 kilometers to just 20. The collapse is so violent that protons and electrons are crushed together to form neutrons. The core becomes a neutron star, a city-sized object so dense that a teaspoon would weigh as much as Mount Everest. Neutron degeneracy pressure, a quantum mechanical effect, finally halts the collapse. The collapsing outer layers slam into this newly formed neutron star at 30,000 kilometers per second and bounce back, creating a shockwave that races outward throughout the star. This is a supernova, one of the most energetic explosions in the universe. The numbers are staggering. A typical supernova releases more energy in 10 seconds than our Sun will produce in its entire 10 billion year lifetime. Most of this energy, 99%, is carried away by neutrinos, ghostly particles that barely interact with matter. The remaining 1% is still enough to outshine an entire galaxy of 100 billion stars. But if the core is too massive, more than about 2 to 3 solar masses, not even neutron degeneracy pressure can halt the collapse. There's no known force in the physics that can support such a massive core against its own gravity. The collapse continues past the neutron star stage. The core shrinks from 20 kilometers to 10 to 5. When it reaches the Schwarzschild radius, just a few kilometers across for a stellar mass black hole, it disappears behind an event horizon. A black hole is born. Interestingly, the most massive stars might not even produce supernovae. If the core is massive enough, it might collapse directly to a black hole, without a dramatic explosion, creating what astronomers call failed supernovae, or direct collapse black holes. Once formed, black holes can grow by feeding on their surroundings. In binary systems, they can ship material from companion stars, creating the spectacular accretion disk we discussed earlier. Isolated black holes can accrete interstellar gas and dust, though much more slowly. Black holes can also grow by merging with other black holes, producing gravitational waves, ripples in space-time itself, that we can now detect with facilities like LIGO and Virgo. Each merger creates a more massive black hole and releases enormous amounts of energy in the form of gravitational radiation. The formation of supermassive black holes remains one of astronomy's greatest puzzles. How did black holes weighing billions of solar masses form so early in the universe history? We see these giants when the universe was less than 1 billion years old. Not enough time for stellar mass black holes to grow through normal feeding. Several theories compete to explain supermassive black hole formation. The collapse of the very first stars, population-free stars, into black holes weighing hundreds of solar masses. The direct collapse of primordial gas clouds into intermediate mass black holes. Or rapid growth through super-adding and accretion in the early universe's dense moments. Black holes aren't just massive objects sitting in space. They're natural laboratories where the most extreme predictions of physics play out in ways that would be impossible to create artificially. They're cosmic testing grounds for our deepest theories about the nature of reality. Let's start with something that sounds like science fiction, but is also real. Gravitational time dilation. Time literally runs slower in stronger gravitational fields. Near a black hole, this effect becomes extreme. Imagine you and your twin approach a black hole together. Your twin hovers at a safe distance while you venture closer to the event horizon. From your twin's perspective, your clock runs slower and slower. Your movements appear sluggish, the light from your spacecraft becomes redder and dimmer as it climbs out of the gravitational well. But here's the mind-bending part. From your perspective, time seems normal. Your clock ticks at the usual rate. It's the outside universe that appears to speed up. You might watch your twin age years in what feels like minutes to you. This time dilation is intimately connected to gravitational redshift. Light climbing out of a gravitational well loses energy, becomes redder. Near a black hole, this effect becomes so extreme that light from just above the event horizon is redshifted almost to nothing, which is why black holes appear black. As you approach a black hole, you would experience tidal forces, differences in gravitational pull between your head and your feet. For stellar mass black holes, these become lethal long before you reach the event horizon, stretching you vertically and compressing you horizontally until you resemble cosmic spaghetti. Paradoxically, supermassive black holes are gentler. Their event horizons are so large that tidal forces at the horizon itself are relatively mild. You could potentially cross the event horizon of a supermassive black hole and survive for some time before the increasing tidal forces tears you apart. In the 1970s, a young Stephen Hawking made a discovery that would revolutionize our understanding of black holes and fundamentally changed perspective on physics. He found that black holes aren't completely black, they glow. Hawking's insights come from quantum mechanics. The vacuum of space isn't empty, it's fizzing with virtual particle pairs that constantly pop into existence and annihilate each other. These quantum fluctuations happen every time, all the time. But near a black hole's event horizon, something remarkable happens. Sometimes one particle from a virtual pair falls into the black hole, while the other escapes. The black hole effectively pays the escaped particle's energy by losing a tiny bit of mass, shrinking slightly in the process. This Hawking radiation gives black holes a temperature. And here's the cosmic joke. The more massive the black hole, the cooler its temperature. A black hole with our sun's mass would have a temperature of 60 billionths of a degree above absolute zero, colder than the cosmic microwave background. It would also take 10 over the power of 67 years to evaporate completely. vastly longer than the current age of the universe. But smaller black holes are hotter. A black hole with the mass of a mountain would have a temperature of trillions of degrees and would explode in a fraction of a second, releasing the energy of millions of hydrogen bombs. Hawking radiation created a crisis that still keeps physicists awake at night. Quantum mechanics has a fundamental principle: information can never be truly destroyed. It can be scrambled, hidden, or transformed, but never eliminated entirely. Think of burning an encyclopedia. Even though the book is destroyed, in principle all the information it contained still exists in the exact arrangement of smoke particles, ash, and heat radiation. Given perfect knowledge and impossible computational power, you could reconstruct every word. But black holes seem to violate this principle. If you throw that encyclopedia into a black hole and wait for the black hole to evaporate through Hawking radiation, where does the information go? Hawking radiation appears to be completely thermal, random, carrying no information about what fell into the black hole. This information paradox has spawned decades of research and exotic theories. Maybe information leaks out in subtle correlations in the Hawking radiation. Maybe black holes don't have singularities and information bounces back out. Maybe the paradox reveals that space and time are emergent properties of something more fundamental. One of the most mind-bending potential solutions involves the holographic principle, the idea that all the information in a black hole's interior is encoded on its two-dimensional surface, like a hologram that contains a three-dimensional image. This principle has no profound implications beyond black holes. It suggests that our three-dimensional perception of space might be a projection of information stored on a distant two-dimensional surface, that reality itself might be holographic. Black holes obey laws remarkably similar to thermodynamics. They have temperature, Hawking radiation, entropy, proportional to their surface area, not volume, and they follow conservation laws, analogous to the laws of thermodynamics. Jakob Bekenstein and Stephen Hawking showed that the black hole's entropy is proportional to the area of its event horizon, not its volume. This was revolutionary. It suggested that the maximum information content of any region is determined by its surface area, not by its volume, leading directly to the holographic principle. Recent developments in the information paradox have led to even more exotic proposals. The firewall hypothesis suggests that some quantum mechanics might create a wall of high-energy particles right at the event horizon, incinerating anything that tries to cross. Other theories propose that entangled black holes might be connected by wormholes, creating a web of space-time connections that could resolve the information paradox while revealing deep connections between quantum mechanics and gravity. While we can't create black holes in laboratories, we can observe them to test our most extreme theories. The detection of gravitational waves from black hole mergers is already providing new tests of general relativity in the strong field regime. Future observations might reveal signatures of quantum gravity, firewalls, or other exotic physics. For most of the 20th century, black holes existed only on paper. Solutions to Einstein's equations that seemed too extreme to be real. How do you observe something that by definition doesn't emit light? The answer came through one of the greatest detective stories in astronomy. The breakthrough began in the 1960s with the dawn of X-ray astronomy. Rockets carrying X-ray detectors discovered intense X-ray sources scattered across the sky, far too energetic to be explained by normal stellar processes. The most famous of these was Cygnus X1, discovered in 1964. Astronomers found it was part of a binary system, a massive blue supergiant star orbiting something invisible every 5.6 days. The invisible companion was pulling material from the visible star, heating it to millions of degrees and making it glow brilliantly in X-rays. By studying the orbital motion of the visible star, astronomers could calculate the mass of its unseen companion. The result was shocking, at least 15 times the mass of our Sun, far too heavy to be a white dwarf or neutron star. By the early 1970s, most astronomers were convinced that Cygnus X1 harbored a black hole. Discovery was so controversial that Stephen Hawking famously bet Kip Thorne that Cygnus X1 wasn't a black hole. Hawking later conceded to bet, admitting that black holes were real, a concession that would prove prophetic given his later work on black hole thermodynamics. But the most dramatic breakthrough in black hole observation came from an entirely different approach. Listening to space-time itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, was designed to detect ripples in space-time caused by the most violent events in the universe. On September 14, 2015 at 5 a.m. Eastern Daylight Time, LIGO detected something extraordinary. For 0.2 seconds, both LIGO detectors in Louisiana and Washington felt space-time stretch and compress by less than 1/10,000th the width of a proton. But it was enough. The signal, dubbed GW150914, showed the unmistakable signature of two black holes spiraling into each other. One weighed 36 solar masses, the other 29. When they merged 1.3 billion years ago, they created a new black hole weighing 62 solar masses. The missing 3 solar masses had been converted entirely into gravitational wave energy. The numbers are mind-boggling. At the moment of merger, the gravitational waves carried more power than all the stars in the observable universe combined. For that brief instant, this collision was the most energetic event occurring anywhere in the cosmos. Since then, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, revolutionizing our understanding of these objects. We now know the universe is teeming with black holes, that they merge regularly, and they have some masses we never expected to see. But perhaps the most iconic breakthrough came from an even more ambitious project, photographing a black hole directly. The Event Horizon Telescope, EHT, isn't a single dish but a planet-sized network of radio telescopes working together to create Earth-sized virtual telescope. The team's first target was M87 star, the supermassive black hole at the center of our galaxy, about 55 million light years away. Despite being incredibly massive, 6.5 billion solar masses, it appears tiny from Earth, about the size of a grapefruit on the moon as seen from Earth. The technical challenges were immense. The telescopes had to be synchronized to a billionth of a second using atomic clocks. Weather had to be perfect at sites around the globe simultaneously. Mountains of data had to be processed using sophisticated algorithms to reconstruct the image. On April 10, 2019, the world saw the most impossible, the first photograph of a black hole's event horizon. The image showed exactly what Einstein equations predicted, a dark shadow surrounded by a bright ring of glowing gas, warped and magnified by the black hole's immense gravity. What we are seeing isn't the black hole itself, but the shadow it casts against the glowing accretion disk behind it. The bright ring is light from gas orbiting the black hole. Some of it bent around the black hole's speck side by gravitational lensing, creating a cosmic magnifying glass effect. The team's follow-up achievement was even more challenging. Imagine our own galaxy's supermassive black hole, Sagittarius A star. Though much closer, it's also much smaller and changes much faster, making it trying to photograph a small, hyperactive child compared to M87's large, relatively sedate adult. The Sagittarius A star image released on May 12, 2022, confirmed that our galaxy's central black hole looks remarkably similar to M87 star, validating our understanding of black hole physics and Einstein's theory of general relativity in extreme conditions. We're now entering the era of multi-messenger astronomy, using gravitational waves, light, neutrinos, and cosmic rays together to study black holes. Each type of radiation carries different information, creating a more complete picture than any single method alone. The future promises even more spectacular discoveries. Space-based gravitational wave detectors like LISA will detect mergers of supermassive black holes billions of years ago. Next generation Event Horizon telescopes will create movies of matter falling into black holes, possibly revealing new physics in the process. Through gravitational wave detections and X-ray observations, we're conducting the first cosmic census of black holes. We now know stellar mass black holes are more common than expected, with typical masses higher than we predicted. The mass gap between neutron stars and black holes might not exist as clearly as once thought. LIGO has revealed exotic mergers involving black holes with unexpected properties, some spinning in opposite directions to their orbits, others with masses in previously forbidden ranges. Each detection teaches us something new about stellar evolution, supernova physics, and the cosmic assembly of structure. Black holes don't just live in the equations of Einstein or the detectors of LIGO. They haunt our stories, our fears, and our imagination. The idea of a cosmic abyss that devours everything in its path is older than science itself. Long before astronomers proved black holes were real, storytellers imagined the void. In the golden age of science fiction, black holes were everywhere, although often misunderstood. Writers conjured up space whirlpools, cosmic drains, portals to other dimensions. They weren't really just physical phenomena, they were narrative devices. A black hole could swallow a ship or spit one out halfway across the universe. It could be a villain, a prison, or an escape hatch. Star Trek treated black holes as both hazards and gateways. Doctor Who turned them into cosmic engines, and in the 1979 Disney film The Black Hole, they became metaphors for obsession, madness, and the human hunger for power. The physics was often wrong, but the symbolism was powerful. Then came a turning point. Christopher Nolan's Interstellar didn't just use a black hole as a plot device. It brought the most accurate black hole ever simulated onto the big screen. Kip Thorne, Nobel Prize-winning physicist, worked with visual effects team to turn equations into imagery. The rendering of Gargantua was so detailed it produced a new scientific insights about how light bends around spinning black holes. A Hollywood movie literally advanced astrophysics. And then, when the Event Horizon Telescope released the first image of M87 star, people instantly compared it to Gargantua. For once, fiction and reality looked eerily similar. But black holes aren't just science fiction props. They've become cultural metaphors. We speak of emotional black holes, financial black holes, attention black holes. They symbolize the fear of being consumed, of disappearing without a trace. In literature, they echo Dante's Inferno or the abyss in Nietzsche's philosophy. They embody annihilation, transformation, and the limits of knowledge. What makes them resonate is not destruction, but mystery. Black holes remind us that the universe has depth we can't yet fathom. They're not just terrifying, they're magnetic. They pull us in not because we want to vanish, but because we want to understand. When we think of black holes, we imagine them lurking silently in space, invisible and isolated. But at cosmic scales, they are anything but passive. Black holes shape the universe itself. Billions of years ago, young galaxies lit up at quasars, the most luminous objects in the universe. Powered by supermassive black holes, quasars outshone their host galaxies by factors of hundreds. For astronomers today, they are cosmic lighthouses, beaming across billions of light years. They allow us to see the black of the dawn of galaxies, to the first billion years of the universe. But quasars aren't more than spectacles. They're engines of regulation. When a black hole feeds, it doesn't just swallow. It blasts energy outward. Jets of plasma race across intergalactic space, eating and stirring vast clouds of gas. That energy can quench star formation, preventing a galaxy from burning through its gas too quickly. In a strange way, black holes protect their galaxies from growing unstable. Simulations show the difference. A galaxy without an active black hole burns out. Its stars form too fast, its structure collapses. A galaxy with an active black hole maintains balance. It's like a thermostat, regulating temperature by venting heat. Zoom out further, and black holes may have sculpted the very architecture of the universe. Their jets seeded the intergalactic medium with heavy elements, distributing the building blocks of planets and life. The fingerprints of black hole activity are written in the large-scale structure of the cosmos. So black holes aren't just cosmic graveyards. They're creators, regulators, and architects. In their violence, they sculpt the conditions for stability. In their destruction, they plant the seeds of creation. If black holes test the limit of physics, they also fuel its wildest speculations. They are the natural stage for what-if questions. Could black holes be wormholes? Gateways to distant regions of space and time? The math of general relativity allows it. Solutions like the Einstein-Rosen bridge describe a tunnel through spacetime. But the universe is less forgiving than mathematics. Such tunnels collapse instantly unless held open by exotic matter with negative energy density, something we've never observed. Still, the idea persists. Wormholes populate science fiction as shortcuts, time machines, and portals. And physicists keep asking, could the laws of nature hide such doors in the fabric of spacetime? Another speculation, maybe every black hole births a new universe on the other side of its singularity. From our perspective, matter falls in and vanishes. From another perspective, it explodes outward in a new Big Bang. In this picture, our universe itself may have begun inside a black hole in another universe. If true, black holes aren't just ends, they're beginnings. Then there is the mystery of dark matter. Could it be made out of black holes? Not the stellar corpses we see today, but the primordial black holes, tiny relics from the Big Bang. If the early universe produced enough of them, they could amount for the missing mass that holds galaxies together. So far, observations don't rule it out entirely. The possibility lingers. And finally, the question that caused media frenzy. Could particle accelerators create tiny black holes? According to some speculative models, yes. But if they exist, they would evaporate instantly in a puff of Hawking radiation. Far from being dangerous, they'd be a window into an extra dimensions in quantum gravity. These are not certainties. They are working theories, sketches on the frontier. But they matter because they stretch our imagination, forcing us to confront possibilities far stranger than fiction. The next few decades will be a golden age for the black hole science community. On Earth, LIGO and Virgo already hear the songs of colliding black holes. In the 2030s, the Laser Interferometer Space Antenna, LISA, will take this further. 3 spacecraft, millions of kilometers apart, will detect the slow ripples of supermassive black holes merging across the universe. LISA will let us listen to collisions from billions of years ago. Meanwhile, the Event Horizon Telescope is evolving. Instead of single snapshots like M87 star and Sagittarius A star, future arrays will capture movies, dynamic footage of matter spiraling into black holes. We may watch in real time as gas plunges past the event horizon, testing Einstein's theory with every frame. The James Webb Space Telescope is peering deeper into the cosmic history than ever before. Already, it has revealed supermassive black holes in galaxies less than 1 billion years after the Big Bang. Giants that shouldn't exist so early. This is a puzzle that may force new physics. And black holes remain the proving ground for quantum gravity, the theory that will unite relativity and quantum mechanics, string theory, loop quantum gravity, holographic duality. All roads lead through black holes. They are the laboratories of the impossible. We stand at the edge of a revolution. Each new observation is not just about black holes, it's about reality itself. In the end, black holes force us to confront the biggest questions. They are boundaries where time, space, and knowledge collapse. They embody limits. Yet limits are not walls, they are horizons. Horizons invite us to cross them. When we look at black holes, we are not just studying physics. We are studying ourselves, our curiosity, our defiance, our refusal to stop asking questions, even when the answers lie beyond reach. This is where we began. The first picture of a black hole shadow, a ring of light bent by gravity, surrounding a darkness from which nothing escapes. It is, in a sense, a portrait of humanity itself. The image says, we looked into the void, and we did not turn away. Thank you for watching Galactic Gateway. See you next time.